In this paper, we present an algorithm to solve trajectory retiming problems for not only the time optimal objective, but also for quadratic objective functions. First, let's give a quick introduction to the retiming problem. In this problem, we're given a path q, and we're trying to find the optimal function s of t, which describes where along the path we should be at time t, to satisfy some constraints and objectives. The most common cost function to use is the total duration of the trajectory, but this is often suboptimal because it saturates control and state limits to maximize speed. As a simple example of a situation where this is undesirable, consider a machine shop which seeks to increase its production rate, but not at the expense of wearing down its tools prematurely. As another example, consider that operating at the control limits will leave no margin for a closed-loop controller to correct against any disturbances. One approach to resolve this issue could be to reduce the control and/or state limits to build in some safety margin. But tuning this is finicky because too much margin causes infeasibility, while too little margin causes lack of stability. Using our proposed algorithm, you can solve the retiming problem not only with the time optimal objective, but also with quadratic objectives. In this example, we set up a cable-driven parallel robot problem with tension limits. In the time optimal solution on the left, the cables frequently saturate the tension limits, which results in times when the closed-loop controller loses controllability. If instead we use the quadratic objective shown on the right, the closed-loop controller will have much more margin to work with. Here you can see our experimental setup of a planar cable-driven parallel robot. The end effector is the white square with black outline, and the 4 cables are highlighted in blue. In this video, the robot traces out the star shape using the time optimal parameterization. We can observe 2 things. First, the end effector shakes and bounces quite a bit. Second, the end effector deviates from the nominal path, especially at the top left of the star. It's a little bit difficult to see, so let's annotate the video with motion trails. Notice here on the 3rd vertex of the star how the robot doesn't decelerate fast enough and carries extra upward velocity into the next edge. To understand what's happening, let's take a look at the nominal cable tensions. Now on this robot, I happen to know that the bottom right cable, which is cable 1 in black, has some extra friction in the system. If we observe the plot on the top left very carefully, which is the time optimal parameterization, we can see that at the third vertex, cable 1 is asked to pull with the maximum allowable tension. Due to friction, it can't quite achieve this full tension. Furthermore, its primary antagonist cable, which is cable 3 in green, is at the minimum allowable tension, so it cannot loosen up anymore to help decelerate the end effector. As a result, the end effector is unable to fully arrest its motion and continues with an upward trajectory on the following edge. Contrast with this with the quadratic objective solution on the right, which balances both the speed and the margins to the tension limits. As a result, all the cables have plenty of margin for the closed-loop controller to compensate for friction and other non-ideologies. Now we show the video of the solution with quadratic objectives and with motion trails. Finally, here's the 2 trajectories side by side, and with motion trails. Thank you for your time, and feel free to check out our code linked in the paper.